Now we can ask a more interesting question. How do I build, let us say, uh, 7 is to 2 power 7. So what is this? 7 is to 2 power 7 is how many? 128. Decoder. Okay. But using the 3 is to 8 decoder that we have built. So we are now going to build this entire 7 is to 128 decoder using this 3 is to 8 decoder that we had already built, of course with enable. Okay, I will say with enable. Okay, so now let us look at what is this truth table first of all. Okay, 7 is to or maybe we can start, no, we'll just proceed with this, right? So this is maybe I'll make it a 6 is to 64. Okay, I'll just add 2 more, 3 more bits. Okay, so I'll do A5, A4, A3, A2, A1, A0. Okay, and my outputs are going to be Y0, Y1, Y2 all the way to Y63, and of course I have an enable here for this decoder. Okay, even this decoder is with enable always. Okay, and you will see why the enable is very necessary or very essential in order to build such higher decoders. You will see that in this thing. So as usual, it doesn't matter what the 6 inputs are, everything has to be 0. Right, this is essentially everything has to be a 0 here, right? And then we have 1. Okay, A5 is the MSB, so let's say 0 0 0 0 0, Y0 will be high, 1 0 0 0 1, Y1 will be high. Okay, 0 0 0 0 1 0, Y2 will be high, and so on. You go on like this for all the 64 combinations. 1 1 1 1 1 and 1 will result in Y63 going to 1, and of course, sorry, here Y63 going to 1 and everything else being 0, Y62, yeah. Okay, so effectively this is the truth table that we want, but we are limited by the fact that we have only a 3 is to 8 decoder, right? We cannot use anything else to build this circuit. So let us look at how we could do this. Okay, so the first thing is, if you look at just A2, A1, A0, so you look at this, right? If you focus just on these 3 bits and look at it, right? So A2, A1, A0 are just 3 bits and therefore it can go through 8 combinations. But there are 64 combinations here when the enable is 1, right? And therefore it will cycle through all the combination 8 times. Okay, and what does that mean? It basically means that in each time it goes through the 8 combinations, right? 0 0 0 to 1 1 1, it is simply going to pick out different things. So let us look at just this combination. Okay, A2, A1, A0, this is going to go through 8 combinations: 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 1 0, 1 1 and 1. Okay, now depending on the other 3 bits A5, A4, A3, right, which each of them can independently go through 0 1 combination, and hence they have 8 combinations. For each of those 8 combinations, A2, A1, A0 will go through its own 8 combinations. Okay, so if you just focus on this A2, A1, A0 being 0 0 0, what are the bits that can go high, right, at the output for this combination. That's all I am asking, right? So clearly it is for all 8 combinations. So first of all, Y0 can go high, right? Then you can have, after that you will have Y, am I, so 0, yeah, it will be 8, Y16, Y24, Y32, Y40, 48, right, Y56. Okay, these are the outputs that can go high when A2, A1, A0 are 0, 0, 0. Okay, and each of these get determined by the combination of A5, A4, A3. So for example, if you take Y8, the combination of A5, A4, A3 must be 0, 0, 1, right? Then the 6-bit number will read as 0, 0, 1, 0, 0, 0, which is 8. Okay. Now, likewise, when you have 16 or when you have 40, let's look at 40. Okay. A5, A4, A3 must be 0, 0, 0, 4, 5, right? So this must be 1, 0, 1, right? So why is this? Because it is 2 power 5 plus 2 power 4, 2 power 3. Yes. Okay. So when A5, A4, A3 is 1, 0, 1, then Y40 has to go high, right? This is how the whole the behavior is. Now likewise, when you go to A2, A1, A0 being 0, 0, 1, we are trying to see what outputs will go high when A2, A1, A0 are 0, 0, 1, right? Likewise, there are 8 combinations because of A5, A4 and A3, and therefore this will be Y1, Y9, Y, let's see, Y16, no, Y17, therefore Y25, like this all the way to Y57, right? Finally, if you look at this, it will be Y7 plus 8, Y15, 23, sorry, Y, sorry, Y7, yeah, Y15, Y23, Y, um, 16 plus 7, 24 plus 7 is 31, all the way 57 plus 7 should be Y63. Is that right? Y0, Y8, Y16, 56. Okay. 0 plus 7, 56 plus 7, 63. Yes. Okay. So these are the outputs that have to go high when A's A2, A1, A0 essentially are, there are 8 combinations. So therefore, what you can do now is the following. You can think of this as the last stage of the decoder, right? I am going to build, each block is a 3:8 decoder like this. Okay, and no, I'll draw it a little more, I'll draw it a little bigger so that internally I can label these pins. Okay, so this is 3:8 decoder. Okay, A2, A1, A0, Y0, Y1, Y7. Okay, and I have the enable signal here, right? So this is my enable signal, um, En. Okay, now what I want to do therefore is to figure out how to connect these decoders together, okay, such that these this higher 6:64 decoder can be built. Okay, so if I so what I'll do is I will also maybe reorder these pins a little bit. Okay, um, I'm going to reorder this thing a little bit. Okay, I'm going to just change this symbol, okay, in the following manner. So I will give my inputs A2, A1, A0, okay, and the enable will come from here, okay, and then I have my outputs Y0 all the way to Y7 coming from here. Right. So this symbol that we have drawn for the decoder, right, we had just conveniently represented the inputs on the left and the outputs on the right and the enable on the top. Really, there is no sacrosanct rule to do this. The symbol is just a representation of that block, and therefore it doesn't matter where those pins are placed. That is going to be placed as per our convenience of drawing the schematic or drawing the logic diagram that we will see now. Okay, so I will consider, I will, instead of writing this internal block of A0, A1, A0, right, and Y0, Y2, Y7 and all that, I will just put 3 pins here and 8 pins here, right, and 1 pin here, which is called the enable. Okay. Okay, I'm just going to represent it like this. So this means it's a 3:8 decoder. Okay, so we are going to go ahead and build our 3:8 decoder using this symbol. So let me make a copy of this. Okay. So first of all, what you see is there are 8 sets of, for each A2, A1, A0, there are 8 such, outputs that are possible. And how many such decoders do I need? As many as A5, A4 and A3 can go through their combinations. Okay, so therefore those are 3 separate bits, and therefore if I want a final output of 64, the decoder to have 64 outputs, then I need 8 of these 3:8 decoders at the output stage, because only then will I get 64 outputs. Okay, so let me just okay. So what I'm going to do now is, this is my Y0 of my Y1, Y7. Okay, this is my decoder that I am basically the pins that you see Y0 to Y7 are that of my 6:64 decoder here. So we are talking about a block which is now like this. Okay, so 6:64, right? So therefore I will have A5, A4, A3, all the way to A0, Y0, Y1, Y63. Okay, this is my 6:64 decoder block that I am talking about. Right, so this essentially means, exactly like what we saw earlier in the 3:8 decoder being used to implement a 2:4 decoder. This means that the Y0 pin of our 6:64 decoder is connected to Y0 of that decoder D0. So let me also label these, give it a number, right? Let me call this D0. This is D1 and D7. Okay. Now what am I going to do? I am going to simply connect all these inputs to A0, A1, A2, right? So this is, I have dot 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 here. Let me just move that a little lower. Right? Yeah. So this is decoder D1. So these inputs I am going to call A0, A1, A2. Similarly here A0, A1, A2, right? And here I will say this is Y8, okay, Y9 all the way to Y15. Finally, this is going to be the last thing, Y63. So what was this output there? 56, right? Y56, Y57, right? And then dot dot dot. Okay. So what you see now is, just observe each of these decoders D0 to D7. When A0, A1, A2, right, are 0, 0, 0, it is possible that only one of these decoders or all or many of these decoders, depending on the enable signal, for its Y0 signal to go high, right. So if you look at this, if this is 0, 0, 0, either this could go high, this, that depends on that decoder's enable here, right, what this signal is. Okay. So we'll have to now make the connection so that we get the desired behavior based on this. But you are now able to see the mapping that we did here, right? Y0, Y8, Y16. Okay. So when it is 0, 0, 0, it is Y0, Y8, Y16 all the way to Y56. When it is 0, 0, 1, you have Y1, Y9 and so on, right? You just go on like this. So now the question is, how are we going to basically, get this, this whole connections done so that the enable of these decoders are turned on appropriately. Okay. So now let us go back and again look at this truth table, right. So we look at what happens, to this truth table. So when we have, let me copy that truth table again now, okay. Okay, so now what we are going to do, we are going to just focus not on this inner block, okay, we are going to focus on the outer block, which is basically A3, okay. So if you look at, the first 8 combinations, let me rewrite that alone, okay, 1, 0, 0, 0 1 2 3 0 1 1 1 0 0 sorry 1 0 1 1 1 0 1 1. Okay, and then I am going to continue this all the way to 1 1 1 0, I mean 1 1 1, in which case y63 will go high here and everything else will be 0 0 0 and so on, right. So if you look at just this, right, at 1 1 1 y7 will go high, right, some y7, if y7 is here, y7 will go high, exactly, right. So for each of these combinations, when 0 0 0 is actually being when A5 A4 and A3 are 0 0 0, the one of the decoders has to basically be enabled and y0 to y7 will have to go high, right. So if I look at this guy now, right, I will basically have to, let me make a copy of this. Right. So now what I do, I am going to go ahead and connect A5, A4, A3. The higher order 3 bits I am going to connect here. Okay. And then what I will do is, I will connect this decoder with the enable. Okay. So the real question is, we'll come to where the enable of this decoder should be connected. Okay. So if this is connected to 1, for example, logic 1, then A5, A4, A3, suppose that goes, is 0, 0, 0, then we know that this output will go high. And we already know that when that happens, what we need is effectively the first decoder D0 to get activated, right. So therefore, I will say that my enable for this decoder must come from this thing. Okay, so what this means is, I'll call this decoder D8. D8. Okay, that's my decoder D8, right? And what it's basically saying here is, I have connected the pins A5, A4, A3 to the internal pins A2, A1, A0 of the 3:8 decoder, right? And the output Y0, right, of D8 is now going to the enable of D0. Likewise, when A5, A4, A3 are 0, 0, 1, the next decoder has to get activated, right. If you write the truth table, you will see it for yourself, and therefore the Y1 of D8 must now go as an enable to the enable signal of D1. Finally, the Y7 output of D8 must go as okay. So this is effectively the behavior or the schematic of a 6:64 decoder using 3:8 decoders. Finally, I need to control that this entire decoder, right, with an enable signal only when enable is high. So therefore, the first primary input decoder I will connect to the enable. So the enable of the decoder D8 is what I am going to connect my enable signal to, Okay. Now this is if you just look at this whole thing again, when enable is 0, okay, En is 0, D8, none of the outputs of D8 will go high, right? Because that's the behavior of that 3:8 decoder. And if none of the enables go high, then none of the enables of D1 to D7 can go high, and therefore none of the outputs Y0 to Y63 can go high. Okay. Now, on the other hand, if enable is 1, then depending on A5, A4, A3, at least one of the 8 decoders D0 to D7 will get turned on, will get enabled, and depending on the combination A2, A1, A0, one of the outputs will definitely go high, right? So now you also see why we built this decoder itself with an enable signal, because without this enable I cannot do the second level decoding. Okay, so this, by the way, is called hierarchical design. It's a hierarchical, so you basically go in a hierarchy. You build a block that is useful and then use that block to build other complex blocks. You don't always think in terms of the elementary logic gates. Okay, so because think about it, having built this 3:8 decoder, right, it becomes much easier, not just from an effort perspective, but sometimes even from an area and a timing perspective, to actually use this block. We use this block to build, because think about it, right? How would you build a 6:64 decoder with just logic gates? Okay, imagine if I had to do this with just AND or inverter that I have in the standard cell library that I showed you in the beginning. 2 input, 3 input, 4 input, right? Then it becomes very complex, because each Y0 Y to Y63 will have to be the output of a 7 input AND gate, right? Enable and 6 other inputs, A0 to A5, right? And therefore that is not going to be feasible to even do, because the 7 input AND gate now has to be broken into 4 input AND gates, 3 input AND gates, and so on, right? Therefore it makes a lot of sense to be able to simply think in terms of this whole hierarchical designing paradigm. Okay, that's the basic idea that we have here. And of course this idea can easily be extended to a 7:128 decoder and so on, right? So therefore what we see now is we needed D0 to D7 8 decoders, right? 8 plus 1 decoder. 8 plus 1 decoders. Which decoder? 3:8 with enable, to implement a 6:64 decoder, right?